Okay. I'm back. Okay. Now, just want to go straight away to the vector calculus. Today, in this video, I want to show how did we get this scalar product. That is C, vector C dot and A cross B. So, why we want to know what is the reason this one is, let it see, if vector C is C1, C2, C3, and vector A bar is A1, A2, A3, and this one B1, B2, B3. So we can write like this. So we want to know why is this. And B1, B2 using determinants. So last video, wanted to walk through quickly. In the last video, I tried to show what is the reason, what is the cross product of two vectors. So if you have two vectors W and let's say this is V, I think in my video I have taken this as A and B, and you can see because there's a A1, A2, A3, these are the component form for vector. The first one, because this chart is already created, I'm just trying to show. So this one is the two vectors are given, the blue and the black. So then what did we do is we try to create a parallelogram using these two vectors. We created a parallelogram this way. And then we try to find what is the area of the triangle. So that was we did. And using that area triangle, okay. So this area, we've seen that it is if I drop this perpendicular from here, when you drop a perpendicular, and then the area of the triangle is base area times the height, and this part is, because this is theta, this becomes magnitude of this one, the V magnitude times sine theta. Okay, so that's what I showed, and then also you see this is the base, so area of the parallelogram is the base is, that is this W bar, so W bar, and then this one and sine theta. So you kind of get some number. So this is the number, and using this number we create a vector which is perpendicular to both the blue and the red and the black graph. So we create this new vector green. So the green vector is created. Okay, so that we understand that it is the vector created. We could have had a vector anyway direction, this one, the same magnitude, whatever that we have. It could be this way also, but I'm taking the one that is perpendicular to both the black and the blue, and then I call this as V cross W. So what is basically cross product is, it is a vector which is perpendicular to both the given vectors. And then we have seen also, I also proved that this vector, the magnitude is this one, and in the component form there is a nice relation. This part can be also obtained using the component. So in this point which is here, I've shown that it shows in the component form this vector, the cross product vector is A2 B3 minus A3 B2, and I proved this in the earlier video. And that can be put, once you get this one, the determinants can be used to represent this one. Of course, this is in the component form, and when you times this times I plus this times J plus this times K, and that's what I wrote here. See, this is the vector, the actual vector, but you can use the determinant also, and you end up getting the same thing. Watch this. So last video, it was in the component form. We proved it why it is, and we can write it in the linear form like this. See, this is the linear form. And then also you can put in the determinant form ijk, and you put the first vector a1, a2, a3, this one, and put the second one, and you work on the definition of determinants to figure out, and you end up getting the same thing. So basically, this part is the magnitude. So the magnitude of this one, this is the magnitude of the green vector, and it is all, which could be also obtained by just using this component. You can take the square root of each one. You can take some of the squares of each of this and get it. So that was done in the earlier video. Let me go further now. How do I use this? So how does this helps to find the volume of a parallelepiped formed by these two vectors? I'm going to use the first two vectors, the blue and the green will be the same one. Let's say the blue and the green. I hope I'm doing it right. So this is the vector, and then the black vector. Okay, so this is, now this time instead of W and B, I'm going to call it as B. So I'll call this vector as A. So now this vector is A. So this is A1, A2, and A3. So this is the component form for that vector until here. This is a vector B, and the component form we'll call it as B1, B2, and B3. So that is, now next is the A cross B. I'm going to use the green vector. So what is A cross B? It is a vector that is perpendicular to both this vector starting from here. So there you go. So maybe this is the one. Call this as vector. So this is vector A cross B. So this is A cross B vector. Okay. Of course, its magnitude is AB sine theta. We can find that too, but my goal here is just to make sure we understand this, that this cross product is perpendicular or orthogonal. So the another word is perpendicular vectors we call orthogonal. That means they are perpendicular. They make 90 degrees. This one is 90, and this also is 90. So this box should have. Now, once we have this, the next is there is another vector, C bar. So let's say there's another vector, and just to get a good in the sense, I want to get a nice figure. I'll take this off. We know it is what vector. Just to make a room here, there's another vector C. Let's see, and not in the plane of this. So, but before that, let's finish this. So because this is because we can create a parallelogram. So that's what we did last time. So we can create a parallelogram. So until here maybe. Okay. So and then join this. Okay. So and this area, we know, we have seen that it is A, so it's the vector A bar, magnitude of this, times the magnitude of the second one, this one, and the angle, let's say this is theta. So I'm going to use this arrow to show the angle is rotating in counterclockwise. So this angle, let's say this is the vector, see this is the vector, so the angle is to consider from here to here. So when you write A cross B, basically when you cross AB, the vector, the green vector, this vector, when you rotate this in the counterclockwise direction, so and you will see this vector goes up like this. That's how the vector goes, A cross B. So A cross B, as you move this towards, when you move A cross B towards B, then this is what happens, the vector is getting formed. So this part, so A cross B is a vector which is perpendicular to both this, the first one and the second one. So the angle here is going in the, if you see this part is in the, so you're going this way. So this is the angle. They form right hand, right angle. So if you go this way, this, so this goes. But if this one goes other side, so if you rotate, so if you rotate B over towards A, then if this goes this way, now there are two different things here. One is you're going this side, this is counterclockwise direction. This is clockwise. It's like a screw. If you try to tighten the screw like this, see when you tighten the screw, like you're clocking and it goes up, right? So it's like you're going, if when you go towards this one, this goes up. But if you are going from here to here, that's the time the vector is on the other side direction. So this part, so now you're going this side, so you're going downwards. So again, counterclockwise is going up and clockwise going down. So the one that we have shown is with the arrow here is this one. So hope you guys are with me, right? Yeah. So the parallelogram is because that's the angle theta. This angle is theta, so we write sine of theta. Now, what is the reason is you can draw a perpendicular here. See this part. So this one is, so that's B bar. This is B bar. This is B bar sine theta. So the area of a parallelogram is this part, because this is the base. This is the base of the parallelogram. That's the height of the parallelogram. So base times height, and you're done. Okay. So next is there is another vector. Let's call that use a blue marker. So there's another vector C. So I'll take this off from here. Just to be, I don't want to show this. Just avoid too many. And there's one more vector here like this, which is a blue color. We use let me use blue color. One more vector like this. So this is the vector. This is vector, let's say C until here. So this is vector C. And using this vector, let's make it a little longer. So using this, we can create a, now using this A, B and this B, we can create a parallelepiped. And what does that means is, like this. So I can use this part from here and go. So whatever this distance I'll have to go this way. I'll try to make it okay. I hope I make it okay. And then the blue one will be this side. So this will be the blue one. So this will be the blue one. Okay. And again from here to here. Okay. And then this one. And then, oh, did I make a mistake? Yeah, this should go and cross. This part will cross. We'll draw a dot here. So that will be the same, parallel to that. So this will be again one more. So I'm going to do that one. Okay, and this will go. Not perfect, but just to get an idea. So somewhere there is some mistake I did. Let me see where there's a mistake here. Okay, so the mistake is here. This should be little slanting. This should be little slanting here. And this goes like this. And this will be a little better now. Okay. Okay. And you can see here, we want to find what's the volume of this. So what I'm going to do is, now that we have used up this, I'll take this off. Okay. And now I'm going to draw perpendicular from, we want to know what is the height of this. We know so what is the volume? So let's write here, volume of the parallelepiped is the base area times the height. And you can see the base area we got, this is the base area, this is the base area, and the height is what we need to know. So that's what the goal is here. For this, now this one is the main A cross B vector. This is A cross. So from here, I'm going to draw perpendicular here. So from this point, you're drawing perpendicular to here, 90. And remember this, when you drop a perpendicular to on the plane of A, and this is the B, which is we don't see this. There is a vector B bar here. So, and this green one is perpendicular to the black and the blue. So what's happening is, this part, what you see is maybe the height. Again, I'm gonna show. The dotted one is right here. Maybe here. So what we are going to do is, let me see, draw it in here. Hope this makes sense. So from here, we want to know what is that height. It's the same this. It may look longer and this looks shorter, but they are the same dotted line. What I'm going to do is draw perpendicular. So if this is black is C bar, the vector, from here you draw perpendicular right here. You get a right triangle. And there's an angle getting formed, call it as alpha. So now this one is on the adjacent of this triangle, this vector is C bar, this vector is C bar. So the adjacent, in this case, so adjacent is always the hypotenuse times, so that means the magnitude. So this becomes the magnitude of this into cosine of this alpha here, right? Almost there. So if you get confused with this, where the hell I got this from, it's because cosine of alpha is the adjacent from here to this. This is what we want. It's the height. So let's call it as like a h. I can call this an h and say this is the height over the magnitude of the hypotenuse has the magnitude this one, and then you multiply this magnitude on both sides, and you get this crosses out, and the height is this one, see, cosine of alpha. Now that we know, so this part also is the same thing. So this is also the height. So that's the height. So this is the height of the parallelogram. Now why I'm showing all these steps is, even I'm taking time is, so most of the time students just do, just use the formula C1, C2, C3, A1, A2, A3, and then B1, B2, B3, and just use the determinant, you know, the volume of a parallelepiped. But my goal here is to show how it works. So I try to show that first. I try to show this part. So this you find the area, and you are using that sine theta thing. So A bar B bar sine theta, and then now that you got C bar, but remember this is what is this actually is the magnitude of the vector. Remember the vector is A cross B. So it is this one what we are going to use. So this part over here, I'm going to write here. This is A cross B and the two lines. So those two lines basically means it's the magnitude of the green vector. Okay, so we got this one. And now all you do is just plug it in here. So right here, base area. So what is the base area? You have A cross B. Okay, so I'm just gonna finish the last part. So what I did is I already had made a chart, beautiful chart here. The one that I drawn is not perfect, but I wanted to show how to make this a perfect parallelepiped. This is the one I tried to do, but it is not that good. It is very shabby. But the idea was to understand this is the area I was talking about. So this is the base area. That base area is it's the magnitude of this green vector, which we got it by being orthogonal to the blue graph, for the blue vector and the green vector. So it is the base area is this, and then multiplication. So that's then the height is. So base area is. We can use the height is right here. C bar that part. That is C bar the magnitude, and times sine. Sorry, it is cosine, right? Cosine of alpha. And then suddenly you should think that, oh, this is like, so this is A cross B, and this is like a one vector. Remember, this is like one, consider it like a vector, single vector. And C is different. C is this one, the green. This is the C. So I think I use the green color. So this part, let me use it like a green vector. Okay, that's the magnitude of this green vector. There's so many colors I use. Okay, and then finally this is by using dot product, or the not only dot product, just the definition. Sorry. So what is the definition using? Definition of dot product. This is A cross B. So this vector, okay, this vector dot. See, so beautiful. So sometimes I forget to put this bar like this. And that's the, now this dot product is commutative. So dot product is commutative. And I can always write this way, and then dot and A cross B. And then you can see it is exactly similar to what I showed here. So what does this means? Basically means you are just multiplying. You're multiplying. And let's see if C was C1, C2, and C3. What's happening is A cross B is right here. Look at this A cross B. Earlier I showed here, it's on the other side. Basically, this C is, let me write quickly, C1, this vector is C1, C2, C3. So I can write in the component form. And the other one, this vector we also seen that it is A2, B3 minus A3, B2, comma, then it is A3, B1 minus A1, B3, and then A1, B2 minus B2, A2, B. So we have also proved that A cross B is that. That's what the last video I showed. And when you talk about dot product, we can use the, here I'm using dot product theorem. So what is that dot product theorem? You just have to multiply this one, the first one to the first one. So it is like, okay, it is C1 multiplied to A2 B3 minus A3 B2. Then you do the C2, that means plus C2, you multiply to the second one. So that is A3 B1 minus A1 B3. And then finally you do again this C3 here, so plus C3, and then this is A1 B2 minus A2 times A2 and B1. And then what is this means? So this basically means, let me take this, I don't need this now because I already have a nice one over there. So what basically this is, if I try to use, let's say if I'm going to use C1, C2, C3, A1, A2, A3, B1, B2, B3, and use the vector, the determinant of this. What's the determinant of this? Is this C1? So that's C1, this C1 into, use this one, so it is A2 B3 and minus B2 A3. Then again this C2, but this time it is this way. You use this one and this one, so it is A1 B3 minus A3 B1, and then plus this C, so C3, so C3 will be this two, so it is A1, so we write C3, and then this is A1 B2 minus. Very good. And finally you see that you use the determinant, you get the same thing, and you, okay, so what's the little issue is here? Watch this. Now there's a minus. We can change this minus. You multiply minus to both. Distribute the negative. So this stays the same. So this stays the same. But now I put plus, and now it is C2, and this swaps. So this goes here, and this goes here. So negative swaps the term. So that becomes A3 B1 minus A1 B3. And you get, and this plus C3, so C3 A1 B2 minus A2 B1. And you will see it is the same thing like C1, it's the same thing. You get C2 and B3 minus A1 plus C3, and you get the formula. So what did we prove here is, that is scalar triple product. It only means if you have two vectors A bar, if there are two vectors A bar and B bar, and then there's another vector C bar, so I'm going to use C bar, it doesn't matter. So what's going on here is, so we got a formula that it is C bar dot A bar cross B bar. Okay, this represents. So what is the conclusion is, this is called a scalar product, and what does it do? It represents. So this represents volume of a parallelogram. The only thing is, just imagine if you have two vectors, these are the two vectors. If these are the two vectors, and you have the third vector is, now remember this, you will have a parallel. This parallelepiped is possible only if this vector, in this case I use W, V, U, but here I use A, B, C. If this is C, if this vector is this way, you see this, if I have a vector which is non-coplanar, so these are on one plane and this is a non-coplanar, you are ending up getting an actual volume. But if this is if this lies on the plane of the, see the speed, so it is a plane, so it's like, suppose all these three vectors, there is one vector and there is another vector here, maybe something here, and here, so this vector, there is no possibility of getting the volume of the parallelepiped, so in that case, so coplanar, so thing you should know is coplanar vectors, so if the vectors are coplanar, then volume is zero. So sometimes we ask, hey, what are the three vectors coplanar? All you do is the same thing, you just do this part and you get the answer. One more thing you have to know is that the cycle, so it means if you do A, B and C, so this C bar, so C bar dot A cross B is same as, I can start with after C is A, so you can write as A, B cross C, or you can write C, B dot A cross B. So all these mean the same thing. So all these are the same thing. They are also written as, this is also written as a box. It means it is C, then A, and then B. So that represents also another way to write. Another way to write this is A bar. So it has to be like a cyclic order. So you can write this way, and this can be written as B, A, and did I make a mistake here? B, C, A. This should be B. If I start with B, then it should be C, and then A. So this will be B, and C, and then A. And the question is why? So if you see this this determinant, if I write this determinant is same as A1, A2, A3, then B1, B2, B3, and C1, C2, C3. That's how you get this one. Or it is also same as, I can bring B up here, B1, B2, B3, and then C1, C2, C3, and then A1, A2, A3. You get the same answer. You can take an example. So if you wish, if you feel that why it is true, you can always check. Just take some number 1, 0, minus 2, 3, minus 1, maybe 4, but 2, put minus 1 and 0, and just change this order exactly like this. So if this could be the vector A bar, B bar, and C, you can change and you see you have the same answer. But if you go this one, so this, if A1, A2, A3, and so if you try to write, instead of this, you write B1, B2, and B3, and then A1, A2, A3, and C1, C2, C3. All you get is the negative of the first one. So whatever this vector here, so this will be your only changing this. It's not in order A, B, C. See, it should have been B, C, A. Now we have B, A. So this becomes minus of C bar like this. So you get, but otherwise the product is the same. The answer magnitude wise, the answer will be same. So yeah, that's all I wanted to say is main thing is why this. So that was the main learning target. So did we got the learning target? So what is the learning target is why this vector represents. In this chart, what I did was I said volume of a parallelepiped there. So instead of A, B, C, I started with the W and then the V, and I used this triangle to get the height of the parallelogram, which is vector V sine theta, and so then okay, the base area is, the definition is of course it's the base is this one, that is the blue one, then the orange one is this height, and then that represents the cross product of this and that. See, these two. And then we say, okay, height of the parallelepiped, so this was the one which I was showing, there was another, u is another vector, of course there I took c, so from here you could figure out this part, adjusted this part, that's the height. So the height of this parallelepiped, wherever it is, it's the same this distance, and this is adjacent to the angle, and that's why you see whatever the hypotenuse, its magnitude times the cosine. So you get that thing, and then you write the formula base area times the height. So this was the base area, and the height is this one, place it, and then suddenly you realize that I take this as the first, that's the first vector, that's the second vector. I hope this helps. Thanks for watching. Remember, thousands of problems could be solved based on this. But the question is, why this form? Why? So why is this? So maybe our question was, why scalar triple product is this one of this? Any one of them, they are all correct. So that was my thought. Okay, so the next one more video I wanted to show you is in the dot product theorem. This is what I the dot product theorem is what I have forgotten is the definition of this is the vector this then cosine theta. But the question is why this dot b bar is a1 a2 plus b1 b2 plus c1 c2. That's the question I wanted to know. Prove why is this true. So that's the next video, because the one that I showed was A cross B is we all know that you just put I, J, and K, you just put A1, A2, A3, B1, B2, B3. But then why? So why do you use this determinant? Because the reason is you know that A cross B is a vector. I can put a vector like this, which is A2, B3 minus A3, B2. Then the next component is A3, B1 minus A1, B3, and then A2, B2 minus A1, B2, and A2, B1. So this is the main thing. This is what helps actually. So the determinant is obtained is only because of this. But all the time it solves problems, thousands of problems just using this. And how did we get? We don't know. And I hope this video helps. How did we get? Why the volume of parallelepiped is the scalar product of scalar, because of eventually you get the answer as a number, real number. C bar is that. Thanks for watching and stay tuned for the next video for this one, why dot product theorem is. Thank you.